Okay, Cat BC, Unit 2, Day 4. This is an extra credit assignment. I'm going to call this 4A. Next one's 4B. These are the answers at the top here. Number 1's B, 2's B, 3's E, 4B, 5E, 6A, 7E, 8B, 9C, 10D, 11C, 12B. The answers in the back. Sort of some free response style problems. Find the zeros. Those are the zeros. There's 4 of them. Equation of the tangent line. Slope intercept or point slopes form. X coordinate of each point where the tangent line is parallel to that line. So we'll check those. And the second one, find the value of k, so f is continuous. It's very similar to problems we've done before. Using that value k, determine if f is differentiable at x equals 2. Use the definition of derivative to justify your answer. It's a little more complicated to use that definition. Let k equals 4. Determine whether f is differentiable at x equals 2 to justify your answer. So those are the answers. So let's go ahead and do these problems. So number 1, if you plug 0 in, you get 0 over 0, which is indeterminate form. So this is the one, though, that we did determine was 1. So I guess we could use that. You could do L'Hopital's rule, which we haven't technically talked about yet, and that would be the derivative of the top and bottom. Cosine t over 1, if you plug 0 into that, you get 1 over 1, which is 1. So that is one way of doing it. Number 2, if you plug 5 in, you get 0 over 0, which means there's probably a hole, and the hole is very apparent here. So the graph actually is the same as the limit of the simplified form, which is 1 over 1, which is just going to be 1 no matter what. So number 3, plug pi over 4 in here, you get root 2 over 2 squared minus 1, which would be 2 over 4 minus 1, which would be 1/2 minus 1, which would be negative 1/2 for your final answer. Nothing tricky there, just some basic trig. Number 4, plug 0 in here. Secant is 1 over cosine. So this is really the same thing as the limit as theta approaches 0 of sine theta cosine theta multiplied by the reciprocal. So it's going to be sine of 0 times cosine of 0 is 0 times 1 is 0. Number 5, the f of x limit is non-existent if f of x equals which of these functions. So which one of these will the limit not exist? Well, if the function is continuous, it should for sure exist. I mean, you could just plug it into this and you say 0 over 5 equals 0. That seems existent. Sine of 0 equals 0. That seems existent. Natural log of 5 seems existent. This one's going to be 25 over 10. That seems existent. This one would be 5 over 25 minus 5 is 0, which would go to infinity. So that's probably the one. The limit is non-existent, so there's like a vertical asymptote there. Number 6, you should be like, oh, that looks like a derivative, the definition of the derivative. So what is the function that we're trying to take the derivative of? Looks like sine x. And this is where the x's usually are. And the derivative of that is cosine x. And then we're supposed to evaluate it at pi over 2. The value that's in there where the x usually goes. Cosine pi over 2 is 0. So take advantage of when they give you a definition of derivative. Number 7, let's see. saying to find the limit as x approaches c. Well, it looks like it's going to be left side, right side don't agree, so we're going to say undefined. One side it's this, other side it's that. They need to agree for the two-sided limit to exist. Next one, for what values of k is it continuous? So that would be the two pieces have to, the limit has to equal the value of the function. So limit as x approaches 2 of f of x is the limit as x approaches 2 of x squared minus 4 over x minus 2, which gives you 0 over 0 in determinate form. But that might be a hole, right? Factor the top, factor the bottom, and we figure out there's a hole in the graph. So if we plug 2 in, there's a hole, but this is what the function is going towards, which means the value at x equals 2 to plug the hole, fix the hole, would have to be k equals 4. So there's a work you could show. Next one, then f will be continuous at x equals 1 if gx equals what? So the left and right sides need to agree. So if we plug 1 in, we get 5. So somehow g of 1 needs to equal 5. So which one of these, if we plug 1 in, will give us 5? That gives you 1. That gives you cosine of 5. This gives you 5. That's looking promising. This gives you 3. This gives you -1. So it's got to be C. Looking for a function that will connect with that other part. If f is continuous on 4 to 7, that's interval notation. How many of the following statements must be true? F has a maximum value on 4 to 7. I would say true. Extreme value theorem. We have endpoints. Right? F has a minimum. I'd say that's true. 7 has to be greater than 4? No, not necessarily. Doesn't say anything about increasing. The limit as x approaches 6 equals the value of 6. Yes, that's the definition of continuity. And they told us it's continuous. The limit agrees with the function. And the derivative dx dy would equal 6x. Oh wait, that's the next problem. So I'm going to say 3 have to be true for sure. Must be true. Next problem, we're taking, looks like this derivative, and it would be 6x. Now technically we should probably write it like that without the dx. But 6x. It's not going to be, maybe some people think it's going to be 3 times 4 squared. Like, oh, I got to do the power rule right there. No, 0, that's just a number. Right, so it's derivative of 0. Okay, number 12, you have a function. Let's take the derivative of the inverse. So this is something we've talked about before, that there's a special relationship. Now, I don't want to actually find the inverse, even though I could. I mean, that is one way. We could just say, oh, okay, it's y equals 2x plus 5. To find the inverse, you swap the x's and y's, and then you solve for the new y. So 2y equals x minus 5, and then divide by 2. And so that is your inverse function right there. So you could then just take the derivative of it, and you would get 1/2. That wasn't too bad, but that's the old school approach. There was a new school approach where we said, you know what, let's just take the derivative of the original function. It's 2 everywhere, which means that the derivative of the inverse at the corresponding point would have to be the reciprocal of this. Well, if it's 2 everywhere, then it's going to be 1/2 everywhere. Well, that's kind of slick. That worked out nice. Otherwise, usually it'd be a little extra work. Okay. Take a look at the problems on the back. (1981). It's a long time ago. AP test has been around a long time. Okay. So this is your function. Find the zeros. Well, zeros are just x-intercepts, which are just where you set y equal to 0 and you solve. Now, this is a quartic. We could try like if it works, x squared minus 1 minus 2. That actually works. So then you get x plus 1, x minus 1, x plus root 2, x minus root 2. And so your roots would be, your zeros would be -1, +1, negative root 2, and positive root 2. So that worked out pretty nice to treat the quartic kind of like a quadratic. Otherwise, you could do rational root theorem. Which more often probably might be the thing you do. So you do your p over q's, and this is your p, and this is your q's, and it's plus or minus 1, plus or minus 2. It's a pretty short list. Try these in here until we get a 0. So if you plug 1 in, hey, 1 positive 1 is 0. And we use synthetic division, zeros for any of the missing terms. And then we drop that first one down. We get 1, 1, 1, 1, negative 2, negative 2, negative 2, negative 2. We should get a 0 at the end if we actually found an actual root and did everything correct. So now it's going to be x minus 1, x to the third plus x squared minus 2x minus 2. And we could do rational root theorem again, or we could try grouping now. It is a cubic with an even number of terms, so that would be an x squared, x plus 1, minus 2, x plus 1. Hey, grouping is going to work if you get the same thing inside both of these. So it would be x minus 1, x squared minus 2, x plus 1. And we're going to get the same results. So, I mean, the first way, obviously, is a quick way. This one wasn't bad. I mean, you could have done rational root theorem again. But we are getting the same answers. 1, negative root 2, positive root 2. So a couple of ways of doing that. Really, that's just algebra. There's really no calculus involved in that. B, write the equation of the tangent line. So we need a point. So we have the x value already. So we got to plug it in to find the y value that goes with it. And so 1 minus 3 is -2 plus 2 is 0. So that's your xy pair. And then you need a derivative to get the slope. So we're going to take the derivative, 4x cubed minus 6x. And we're going to plug 1 into that. And we get -2. So that's your slope. So we're going to do y minus 0 equals -2x minus 1. So this is fine for an answer. Or you could change it to slope-intercept form if you want, which is actually pretty easy this time. Either one. Okay. And then C says find the x-coordinate of each point on the line tangent to the graph f which the line tangent to the graph is parallel. So we want it to be parallel to y equals -2x plus 4, which the main thing is, that means we need the slope to be -2. So we're going to take that derivative that we just found somewhere earlier, last problem, 4x cubed minus 6x, and we're going to set it equal to -2, and we're going to solve this. So it's a cubic. I think this time we are stuck with rational root theorem. Hopefully, if just because rational root theorem isn't guaranteed work if they're irrational answers, but it's going to be p over q. So this is your p's, this is your q's. So it's going to be plus or minus 1, plus or minus 2, plus or minus 1/2, plus or minus 1/4. 2/4 is the same as 1/2. 2/2 is the same as 1. So that's your list. Now, hopefully, it's a nice one. If you plug 1 in, positive 1 works. Nice. 1. It's just going to be 4, 0, -6, 2. Drop the first number down. 4, add. And get a 0 like we should. So we have x minus 1. That's the factor that positive 1 root comes from. 4x squared plus 4x minus 2, which actually reminds me we should have taken the GCF out first. That would have made life a little easier. So I'm going to take it out now. That would have made our P over Q list shorter and made things a little nicer. So I'm going to put that way out in front. And then I'm going to try and factor this by hand. It's got to be a 1 and 1. It's got to be a positive and negative. You can't factor that. So this is one of your roots, but we're going to have to use quadratic formula for the last one. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So negative 2 plus or minus 4 plus 8 is 12. To get square root of 4 out of that, 3 left over. So we're going to get negative 1 plus root 3 over 2, negative 1 minus root 3 over 2, and don't forget positive 1. Those are the x locations where the tangent line to our curve is parallel to that line. Okay, number 2, let f be its function, piecewise function. Part A says for what value k is the function continuous. So we're going to plug 2 into it and see what happens. And we get 5 here. And we get 2 plus k here. And these have to be equal to each other for it to be continuous. The two pieces have to meet. So we solve for k equals 3. Okay. It says justify your answer. So I guess technically, since it's a response, we probably want to say something like limit as x approaches 2 from the left-hand side. Would give you 5, and the limit as we approach the right-hand side of 2. So this is more technical way of proving it. 1/2 x squared, and the k value is 3, so that gives you 5. And so two sides are equal to each other. So that means they agree. And then I guess you would also throw in. So because of that, that means that the limit as x approaches 2 of f of x has to equal 5, the two-side limit. And we also know that the value of the function at 2 is going to equal 5. And so since these are equal, then it's continuous by the definition of continuity. B says, using the value of k found in part A, determine whether f is differentiable. Use the definition of derivative to justify your answer. So I think we're going to take the derivative now, and we get 2 for x is less than 2. We're going to get x, k drops out. So actually k doesn't matter. I mean, it's got to be continuous. And so then if we plug in f prime of 2, both sides give you 2 and 2. This is the lazy way of doing it, right? Therefore, it's differentiable. That's not really using a definition derivative, but we'll let it go for right now. C, same idea, but k equals 4. I don't think it's going to matter because k drops out, right? It's the same derivative. K goes away. Oh, you know what we need to do? Shoot. See, this is tricky. You might be like, oh yeah, look. It's all good. They're both the same. Yay. Okay, but differentiability requires continuity. So we need to check continuity. And so just because the slopes match, so if we plug 2 into that, it's going to be 2 times 2 plus 1 is 5. And then from the right-hand side, it's going to be 1/2 2 squared plus the k value we're saying is 4. So that's going to be 6, and these don't equal each other. So it's not continuous. Therefore, it is not differentiable. it would be better to show the limits. Limit as x approaches 2 from the left-hand side of f of x equals the limit as x approaches 2 from the left-hand side of 2x plus 1 equals 5, and then the limit as x approaches 2 from the right-hand side equals the limit as x approaches 2 from the right-hand side of 1/2 x squared plus 4, which gives you 6. So limit as x approaches 2 minus of f of x does not equal the limit as x approaches 2 from the right side of f of x. So graph is not continuous. Something like that. Okay. Separate video for the next worksheet.